All right, let's pick up next with transition states. I got my green, my blue, and my red. And we are right here at the transition states on page 2986. And here we go. In the gas phase, the existence of a concerted transition state for ARX oxidative addition to Ml2D10 metal centers is well established. Okay, concerted transition state. This transition state is characterized by a three-center interaction involving C ipso, the carbon attached to the halogen, X and M, the metal, C1 in scheme 1, and the concomitant breaking of the CX bond and formation of MC and MX bonds, so metal, carbon, and metal halide bonds. The degree of charge separation at the transition state appears to be rather moderate. Reference, one of the same references. An interesting observation for which a conclusive explanation remains to be presented is that the plane defined by the three reacting atoms, metal, carbon ipso, and X, is perpendicular to the coordination plane LML ligand metal ligand for X equals I, but parallel for X equals F. All right, let's read that again. An interesting observation for which a conclusive explanation, so we don't know why, but it has been observed, is that the plane defined by the three reacting atoms is perpendicular to the coordination plane for X equals I, but parallel for X equals F. Okay, so we do not have F. I wonder why we do not have F. For the related oxidative addition reactions of carbon and hydrogen, silicon and hydrogen, carbon and carbon, carbon and silicon, carbon and germanium, and carbon-tin bonds to Ml2D10 complexes. The influence of various factors, atom type and substitution pattern of the activated bond, type and nature of ligands, metal, on the transition state structure was recently explored. Okay, so all of this paragraph is pretty much background. Here, however, we focus on the transition state in solution, not in the gas phase. We located the transition state TS1, figure 6. What? There's another figure. Yes. Yay, transition states. Uh, figure 6, transition state 1. And transition state 1. All right. Optimized transition state structures in solution. TS1 corresponds to a rotation of the phenyl ring. TS2 to dissociation of the halide. See captions in figures 2 and 3 for explanations. So looking at this, yes. So we're showing a transition state. This actually looks somewhat similar to what we're seeing in our work. Excuse me. Because, wait a minute, the transition state here, this is not what we're seeing. This is not what we're modeling anyway. So it's the transition state has it bonded to the metal, the palladium bonded to the carbon, and the carbon bonded to the halogen. And that's in the plane. So this is perpendicular to the plane, yes. And here we have a tilt, or a different tilt anyway. And we have both of these bonds breaking, or partial bonds. Okay, so this looks like it's both bonds breaking at the same time. Oh, anyway, well, let's see. Maybe they Both happen together? All right. We located the transition state TS1, figure 6, starting from 3,1A, which structurally looks like a transition state of type 1 for a concerted oxidative addition. So TS1 concerted. The activation barrier to reach TS1 from 3,1AX is 39 and 11 kilojoules for X equals Cl and Br respectively. However, following the intrinsic reaction path down from TS1 revealed that this stationary point does not connect 3,1A with 4, but in fact belongs to a ring rotation process converting the 1,2-eta arene complex into the 1,6-eta arene complex. Despite an extensive and careful search, we were unable to locate a transition state belonging to a concerted oxidative addition in solution. Wow. All right. So they found a transition state, but the transition state did not go where they thought it would to the actual product we have. All right. So unable to locate a transition state belonging to as an alternative conceivable only in solution, we then studied the possibility of a dissociative process, that is, dissociation of the halide, followed by collapse to the product. The corresponding transition states TS2 for the dissociation of the halide could indeed be located and were confirmed by frequency and IRC calculations. I do like frequency and IRC calculations. That sounds like something we're doing. They featured a very elongated CX bond and a fully developed PDC single bond, see figure 6. The barrier from 3,1AX, THF, is low. Delta equals 3112 and 5 kilojoules per mole for the different halogens, respectively. Okay, for the full dissociation of the halide yielding separated X minus THF and a cationic other species, phenyl complexes 4 plus THF, the reaction energies are essentially thermoneutral. At the transition state, we find a significant separation of charge. The Aryl halide moiety bears a Hirschfeld charge of minus 0.81 E to minus 0.78 E, slightly decreasing from chlorine to bromine to iodide, of which minus 0.53 to minus 0.48 E are located on the halide alone. These values are to be compared to the considerably smaller charge separation in 3,1A, where the charge on the coordinated Aryl halide amounts to about minus 0.53, of which minus 0.15 E is on the halide. So what does this mean? Also, I see, again, the Hirschfeld charges, I don't know. So we should definitely take a note to look up Hirschfeld. See if I can say that and spell it correctly. Hirschfeld charges, right? Because we always get more questions than we answer when we read these things. So we're making progress. And as far as our transition states go, so this transition state does not lead to oxidative addition in anything that they've found. This one, I think, is going to, but we'll keep reading. Considering these findings, the following picture emerges for the oxidative addition reaction. In solution, the dissociation of the halide from the coordinated haloarene is kinetically and thermodynamically facile, easy. So exothermic, exergonic, what have you. Taking into account entropic contributions will make, so we haven't done entropy yet. That's weird. Will make it even more favorable. So that's why we're doing exothermic, because we're not taking into account entropic contributions. I don't know why, though. And I haven't seen them say it either. Thereafter, the collapse to the Aryl halo complex is an energetically strongly favored and most likely barrier-free process. So that's what we're trying to say with this transition state 2, is that transition state 2 is pretty barrier-free. Let's see. So where's the math on that? Back here, 31, 12, and 5 kilojoules. So yes, compared to the other ones, yes. Those are barriers, but those are much lower than 189 or whatever, I guess. All right, where were we? Yes. Back on screen. Barrier-free process. So most likely barrier-free process. This depiction remains essentially unchanged if one considers that the halide will in reality not be separated to infinity from the complex, but rather form a type of ion pair, okay, not considered in this paper. Whereas the data obtained do not allow us to exclude rigorously the existence of a concerted transition state, also in solution, they suggest that the dissociative pathway delineated here is certainly a very viable and competitive one. So the dissociative pathway delineated here is certainly, I think I left my pen cap off too long. That's not long enough, but. So let's write about that. So dissociative pathway. So it's dissociative pathway, not in very dark text. Need a better blue pen, I guess. Corroborating experimental evidence is provided by the Hammett study indicating a charge-separated transition state. Okay, don't know what that means. The observation of the Meisenheimer type intermediate 2, scheme 1, for orthonitrofluorobenzene fits in as a special case where the transition state is so strongly stabilized by the electron withdrawing substituents and coordination of the night, blah, 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 blah. All right. I think this is looking to other data in the literature to, which is from this 39 and 40. So 39 and 40 had a lot of, like, remember that paragraph about here in the transition state process where they're like, all right, here's all the other stuff that's happened. That was 39 and 40 as well. Those seem to be good reference to get. There's 39. They're comparing a lot of their stuff to 39 and 40. So yes, we won't think about getting 39 and 40. And 39 and 40 are way back here. I'm just going to write on the top. Oh, pen's still dead. 39 and 40. Looks like it still has ink. Shake it down a little bit. That helped a little bit. For a second, anyway. All right, reference 39 and 40. Circle it. And we're almost done. Hours and hours later, we have read one article, almost. All right, I think we're done with that. And let's bang out the conclusions as part of this. We have investigated the oxidative addition Do I have a blue pen? Oh, of course. I have some pen. That's blue or black. It also doesn't work. There we go. All right. It's going to be black, it looks like. All right. So we have investigated the oxidative addition of chloro, bromo, and iodobenzene to palladium zero complexes, bearing the bidentate chelating phosphane ligands, DMPE or BMEP, using density functional theory calculations in combination with a continuum solvation model. This reaction is topical to many catalytic cycles and a fundamental reaction of organometallic chemistry. Almost exactly the same sentence was in the introduction. We considered first the ligand dissociation step, converting the coordinatively saturated PD with two phosphane ligands, bidentate phosphane ligands, into the reactive 14 electron species PDPP, and the formation of different pre-reaction complexes with the phenyl halide attached. With an intact phenyl halide, the formation of the PDPP is strongly endothermic, constituting the most unfavorable of the reaction steps considered here. The following association of the Aryl halide is energetically favored for all combinations of coordination mode 1,2 eta, 2,3 eta, or kappa halide. Halide ligand and solvation state. The Aryl halides preferably bind to an eta squared in an eta squared fashion, meaning to the two carbons, acting as pi acceptor ligands, stabilizing the electron-rich D10 center. So, okay. All right. So we come back to this, I think anyway. So here's the benzene. Here's C. So C here. So what this is trying to say is that this is the LUMO, this is the HOMO, and for the palladium, and that these two are bonding. I mean, I think that's what they're saying. This has electrons, right? So from a Gen Chem sense, I'm not so. This must have two electrons in it. The antibonding. Why would the antibonding have two? So that's a sigma pi star LUMO. C is, wait a minute, okay. So for A and B, for chlorine and bromine, A and B are lower in energy. So A is going to be, come on, Ben. That's the LUMO. So wait a minute. So yeah, I don't think we've talked about this. So if A has nothing to do with the halogen, except for the iodine, I don't know. I don't think they talk a lot about this. I might have to read it again. But yes, okay. So let's go back to the conclusion. Where were we? In the 1,2 eta. So let's go back. The Aryl halides preferably bind in an eta squared fashion, acting as pi acceptor ligands, stabilizing the electron-rich D10 center. So So what we need to know is, what does palladium look like? So my understanding of how these things work is that a ligand brings its pair of electrons to the palladium. So when you lose, but I think I have a very simplistic idea because we've got D8, we've got D10. The D10 has two more electrons, 12 electron. Well, anyway, I have a lot to learn here. But okay, let's read this one more time. The aryl halides preferably bind in an eta. Yes, okay. That's certainly one of their conclusions. Acting as pi acceptor ligands, stabilizing the electron-rich D10 center. In the 1,2 eta complexes, the phenyl halide bond is particularly activated. We therefore consider them as primary precursors for the oxidative addition step, even though it ends up not working. The oxidative addition itself is a strongly exothermic reaction in the gas phase relative to the 1,2 eta arene complexes that profits significantly from salvation, making it another 20 to 40 kilojoules per mole more favorable. So sure. The reaction is even exothermic relative to the stable saturated PD, right, with the sort of one, with the two phosphane complexes, two bidate phosphane complexes, except for the chlorobenzene in the gas phase, which we mapped out ourselves in this picture right here. Right, we said chlorine not favored in the gas phase, was favored in THF, and everything else. Well, we did the iodine. We didn't do bromine. Presumably it will be somewhere, but the bromine gas phase must have ended up below 0. Okay. Regarding the type and structure of the transition state, the concerted transition state reported for the gas phase could not be confirmed in solution. Could not be confirmed in solution. Oh, all right. Okay. However, we found that owing to salvation, the dissociation of the halide is an exceedingly kinetically fissile process. Energetically, complete separation into a cationic phenyl complex and a free halide is essentially thermoneutral, not accounting for favorable entropic contributions. The subsequent recombination of the halide anion with a cationic phenyl complex is then strongly exothermic and most likely barrier free. All right. Considering the oxidation addition process as a whole, it is an easy reaction in the system studied here once the reactive 14 electron species has been generated. Right. After ligand dissociation, which thus constitutes the limiting step, the reaction path is energetically all downhill. All right, that I can go on with. We conclude on with some comments on the usefulness of solvation models for mechanistic investigations. Our studies have shown that even the very basic description of solvation at the level of a continuum model is sufficient for qualitatively new insights to be gained that would not have been accessible through gas phase calculations alone. So solvation is important. Salvation is important. Good, because we're doing salvation for our study. All right. However, it is essential in such work that the salvation model can be applied self-consistently in geometry optimizations. The value of a simple continuum salvation model is obviously restricted to cases where a specific interaction, for example, coordination, of a solvent molecule to the solute is not decisive, right? Because we don't have any solvent molecules here. It's a continuum model. Continuum just means you treat it basically, right, as we mentioned before, as a dielectric material with a certain dielectric constant, but no other properties. Quantitatively, we note that the salvation contribution to reaction energies can be sizable even if only neutral species are involved, up to some 60 kilojoules per mole for the systems investigated here. And that's it. Whew, that was quite a bit. All right, good work. And let me end this.